point here is that what we can do is an expert in the field is here, and we can augment what you already know. Okay, so our lecturer for today is Wei Dai. She's a professor at Rutgers, let's see, her Department of Cell Biology and Neuroscience, and she studies neurodegenerative diseases, Cryo-ET. But the real heart of the matter is that she's been a wonderful collaborator of SEMC, and she's been really pushing cryotomography. And just in general, where we feel, a lot of us feel where EM is moving towards is this resurgence of tomography. I mean, a couple of decades ago, we've been using tomography, but now we're trying to push resolution, we're trying to push use cases, push areas where we can actually go to. And all the advances in cryo, you might have remembered the lectures we talked about, the microscope and all that can be transferred through all the modalities we're talking to. And you'll hear about a lot of that today. And given that you have a bunch of lectures, I'm going to hope that those hands were raised for a good reason, then please do make this as interactive as possible. So here's Wei Dai.
Thank you. Thanks for the introduction. Actually, I have another question to ask you. I know all of you watched the video. Can you use like a one sentence to describe the tomography background? Have you ever done tomography or collaborate with other people who done tomography or read a couple papers or just watch the video so that I know how much I should cover in the discussion? Who are the students? I only need to know.
Students, okay.
Okay, so what's your background in tomography?
Well, we use tomography to see if our protein is interacting with the air-water interface when we do Cryo-EM screening.
So you work with Alex on that, like a nature method.
No, I don't know who he is.
Oh.
I'm very happy to hear this.
Okay. So that's the person you should talk to.
Yeah, well,
Yeah.
with the
They're gonna have
SEMC,
everyone.
actually,
Oh.
yeah.
Okay.
So,
So you know tomography, you've done tomography.
no, I haven't really done per se.
Okay.
But yeah,
Okay.
we use that technique.
Okay. And then who is the second student?
I'm doing tomography on viral machinery, the membrane fusion machinery in 5.8 cystovirus. So I don't really know what I'm doing. I'm just sort of like doing the data processing through Leginon.
Oh, you're doing data processing.
Yeah, so.
So we're advanced user who published a paper on tomography already. That's nice. And then, how about the other?
Yeah. Hi. So I have some background in tomography in that I help some collaborators by processing some tomograms.
Yeah. The other two want to say something, or?
I've never done tomography, but I've been to a couple of talks where they're doing like in situ tomography, like looking at things in like live cells.
I see. Yeah, where's the last one?
I've never done something personally, but I'm familiar with the work that's been done in our lab to look at the arrangement of molecules on liposomes using tomography. So that's how I'm familiar with it, but not personally.
So I think, actually this year the users, they all watch the videos. I'm really surprised. And also majority of them either involved in sample preparation or project with tomography already. So actually I can skip some of the introductions. So outline for today. So I think fundamental, if you want to say introduction to tomography, my understanding, you should understand, when you have a sample, when is that sample ready for tomography? What type of sample would really appropriate for tomography application? What other samples are more appropriate, maybe for single particle or axial crystallography? And then I know in the first session people cover basics in sample preparation for Cryo-EM application in general, probably, but there are several factors or parameters you have to consider specific to tomography. I will try to cover some of them in the lecture. And then lastly, in your syllabus, you actually have lots of concept check questions. So I'm thinking of a good way to organize everything into this lecture and not too boring. So the way what I'm gonna do is I'm gonna set up a case study, pick out one paper and go through the paper from sample preparation to data collection, data processing to see what other parameters, what other conditions they set up. And then I can put all those concept checking questions into that case study. And then I really want to make it into a discussion. we can always control our pace to say, this is the parameter most of the people want to learn more, and then we can just slow down and then look at the details. If everybody clear, we can just go through the whole process. That way, we cover majority of the questions you're supposed to. So what kind of samples? So as already mentioned, tomography seems like really going forward quickly right now. So this is the slide I actually used from last year. So you see tomography, if you look at it, only about 11%, because the total number is about 500 something. So the total number is really low. So I made another slide this year. So the total number increased. The relative ratio of tomography and subtomogram averaging actually increased about 2%. But if you consider the total number of subtomogram averages and tomography, it increased many hundreds of, maybe 300 or 400 of deposition just in 1 year. I see that as a very big step, because last year is only 200 something. This year is 500 more. It's doubled, more than doubled. So it's still a small portion compared to single particle, but it's really going up quickly. So what kind of samples? So many of you has been working on samples of proper wave tomography. So I'm just going to go through really quickly. This is one of the examples for tomography study. It's an ATP synthase in mitochondria. So using tomography, what you will be able to do, you can do subtomogram averaging to get the dimer structure. You can fit the high resolution structure in there to look at how the dimer organized. Also, you can fit the average back into the crystal so that you can see how they form those 2D array on the outer surface. So you can look at structure and then also micromolecular organization in native state. And this is the very famous John Briggs subtomogram averaging. So he is really a pioneer to pushing subtomogram averaging resolution. So I believe this is the paper they published in 2016. What they did was they're really interested in the capsid protein structure in HIV. So what they did was they did tomograms of the whole virion, and then they look at the top view and side view to look at the capsid structures. And by very, very fine-tune all the parameters and control very detailed parameters in their project, they were able to reach like 6, 7-ish resolution by subtomogram averaging. I see that is really impressive. So once you have that resolution, what you can do is you can fit the subtomogram average model into those capsid proteins. So why is it important? So HIV capsid protein is not a new target for structure study. People have been doing it by, for example, Cryo-EM single particle. So what you can do is you can overexpress the protein and then make the tubes like arrays, and then do it by helical reconstruction or single particle reconstruction, and then you can get very high resolution. People have also done actually crystallography study of either the hexamer arrays. So all those techniques give you very high resolution. But remember, the capsid is not a perfect lattice or tube. It's this conical core structure. It's made of hexamers and then pentamers. And then the position of the pentamers are also very variable and special. Only in this situation by tomography, you will be able to see the flexibility, the flexible part, and then the variable parts of different domains in capsid protein. And this is something those hexamer lattice or the tubular structure by single particle will not be able to resolve. So another case, you can look at cells. This is very obvious. Also, I have to say, tomography now is limited in this application because the electron penetration power. You can only look at the edge of it, but still you can get very interesting information out of it. And then also you can look at, for example, biological processes. You can look at phage or baby phages in host cell, and then by looking at the structural feature, you can alter them in their maturation process to understand the biological processes. So that's basically 4 examples I pick up to show really what kind of samples are appropriate for tomography. So if after the first session, we know for single particle, you want to look at more homogeneous sample. Tomography is mostly or more look like, for example, very unique structure or more heterogeneous structure. It gives you the possibility or capability to look at those structures. And also, it allows you to look at structure of biological processes in very complex cellular setting. So this is the first session. What kind of sample, what kind of systems appropriate for tomography? Any questions so far? Okay, clear. So we're gonna go to sample preparation aspect. This I will try to go through really quickly and only emphasize the parameters relevant to tomography application. So all sample preparation for Cryo-EM, we want them to preserve in native state, no ice crystals, and then we want them to still be hydrated so that we can preserve them in very low temperature and we can image them in very high vacuum in the microscope. On top of that, we want to make sure imaging not that hard, so that we want the concentration to be good, and then we also want to make sure the ice thickness is good, the contrast is good, so that you can have those pretty images you can show off. So grid, this I don't know how much you covered in your first session. Probably all of you know hold the grid already in your life. So I only want to make one comment. So there are several parameters to describe what kind of EM grid you want to use for your experiment. So one parameter I want to mention is mesh. Mesh is the parameter to define the number of those squares on your EM grid. For tomography study, because we have to tilt the stage, we want to use grid that with very big square, so that when you tilt it, the bar won't block your view. So for most of the tomography studies, we use 200 mesh or 300 mesh EM grid. For many of the single particle applications, people use 400 mesh. So this is just a small detail. Yeah. So there are two different ways of preserving sample. Conventional, I'm not going to mention at all. So it's not that interesting in this lecture, probably. And then for cryopreservation, so we have plunge freezing, and then we also have high pressure freezing I want to mention, because those are the two mostly used sample preparation procedure for tomography applications. So plunge freezing first. So what kind of samples can be used for plunge freezing? I'm just going to give you a slide to show what kind of samples they are. There you can, from small to large, you can do protein complexes, you can do phage viruses, and then liposome you can do it. And then this is intracellular organelle, vesicles. This is a bacteria, but you will notice the center is very dark already, you don't see much details. And this is a eukaryotic cell. It's a mammalian cell cultured on EM grid. Those are all the samples you could possibly use, possibly freeze, preserve for tomography application. So this is a little bit experimental detail, because when you work in a tomography project, you actually you're probably going to spend more time in front of a bench than in front of the microscope, because you want your sample to be perfect before you want to move to the electron microscope for your pretty images. So this is just an overview. We want to see all our grids like that, right? Good concentration, evenly distributed. But sometimes the concentration is good, but they go to the place you don't want them to be, or on the carbon membrane, or this one is to show all of them show the preferred orientation. There are several issues, many issues. Before you are ready, you have a ready to use grid to put into the microscope. Here I'm just listing a lot of parameters that possibly affect the distribution and concentration of the sample on your EM grid. unless you want to spend some time on it. Otherwise, I'm gonna skip it. This is something, basically, you have to look at several of them. Usually it's a combination of several factors. And then you have to maybe control a couple of them and change a couple of them until you have a good concentration of grid like this.
For the people, how many people have made Cryo-EM grids? Okay, so then this is all making sense, right? So that's over half of the students.
They seem to be pretty lucky. Nobody suffer from this. Otherwise, when I show this grid, you can see people nodding and shaking
No,
their
they're
head.
working on ideal proteins.
They're all good, perfect. And then I want to mention Alex's paper, publication. He used tomography to look at distribution, concentration, basically to check sample quality, grid quality for single particle application. But we can definitely apply this to tomography. So the good practice I have in my lab would be, I have a new sample, I try different conditions, and I screen all the grids I made from different conditions, just small number to start with. And then you could do a tomogram like this. This is the whole, and you can from top to bottom to look at the distribution. This is the Z slider, and you can see overall the ice thickness. Once you nail down the good condition, you go back to the same plunger, set up exactly the same condition, and freeze a bunch of them until you have enough data for the publication. Okay? In some sample, I pick up a movie showing a good concentration distribution. He has, 30-something movies in that paper. Majority of them are not this good looking. So, yeah. So hopefully you don't have to experience this, but very likely you will have to spend your time on this. This is the bad business, okay? So for plunge freezing, in addition to purified protein complexes, you can also freeze cells by plunge freezing. So bacteria, you can definitely do it. The procedure is pretty much just like purified protein complex. You can just put the cell suspension, apply it to EM grid, and freeze that way. Everything I mentioned before apply to that situation. But sometimes you work on, for example, mammalian cell. So there are some extra steps you have to go through before you have a grid for imaging. So for example, first of all, you need to pick up the right grid. I mentioned the mesh number. And also now, when you want to do mammalian cell for tomography application, you also have to consider material, what type of grid you want to use. Usually for majority of, for many single particle applications, you can use copper grid. But for cellular tomography, copper will not be an option because it's great oxidation protein, so the cells are not healthy anymore. We usually use gold grid. And then you also have to consider supporting film for cell to grow on it. So the best support material will be continuous film so that your cell can grow happily on carbon or on silicon dioxide film. But the problem is the contrast will not be that good. So you want to use the quantifoil holy grid, but the hole is not going to give your cell very good support. So this is something you have to consider or try out when you are doing cellular tomography project. So once you have that, you have to very often apply some coating protein to EM grid so that they can grow happier. Because generally speaking, cells, they don't like metal as they like the flasks. So they grow slightly slower and not as healthy as they are. So you have to treat the surface a little bit to make them slightly happier. And then you have to pay attention to the plating density. Make sure you don't have too many of them overlapping. Otherwise, the ice will be really thick. Right. Then you grow for a certain time, and then you freeze the grid, and you can do imaging. This is usually what we do to set up grid plating in my lab. And this is just a representative grid to show you. See, you have that's the cell body, that's lung processes extended out. And then this is the cell, very standard, very representative. So you can see the cytoplasm is relatively thinner. For the edge, this is the cell membrane. For the edge, you will be able to just image directly. So if you're interested in some membrane complexes or interaction to the plasma membrane, you can just image, do cellular tomography directly. But if you're interested in the nucleus or something close to the nucleus space, then there are other tricks you have to do before you can take an image of it because it's too thick. So I know focused iron beam will be covered in the next lecture. So this is the option to make the cell thinner so that you can image. I'm gonna skip it just to show you this pretty picture from the publication. Once you handled everything, that's what you're gonna be able to see. Okay. Okay, any questions?
Everybody can do that.
Everybody can do
No
it.
problem.
It's so standard.
It's very
Everybody
easy.
eventually gets something like that. And then publish on the cover of Nature and Science. That's right. Yeah. So next, we want to talk about high pressure freezing. So for some of the samples, they're thicker. So you want to make sure the whole sample across the thickness be vitreous, for example, patient tissue. And then for that, plunge freezing will not work. You need to use high pressure freezing. So this is the physics. Basically, from this diagram, you can see the phase of water depends on temperature and pressure. So when you apply higher pressure, the ice crystal nucleation temperature dropped. And also the water ice, the ice nucleation is something bad for your sample. You don't want it to occur. So when you apply very high pressure and then also simultaneously apply very high cooling rate, you can delay the process of forming crystal so that you can handle thicker samples in this setup. So once you have the thicker sample frozen on this high pressure freezer that they have one in this center 1 or 2, and then you can move on to a cryo microtube to cut it, thinning, slicing, sectioning, so that you can put it on EM grid. This is also a process, cross-sectioning. I got a movie really interesting from YouTube I want to show. So here is a piece of sample, high pressure freezing, vitreous ice, and then the model at the beginning of the movie, you turn the knob and then you basically move the piece up and down. This is a diamond knife, and this is the vitreous section of the sample you have from that big piece. And then the small fiber used to be eyelash. You basically manually pull out the ribbon. And then this is a ribbon usually like 200 nanometer in thickness. You will be able to apply to EM grid and then do tomography.
You can go down to 50 now.
50. But do you want to do 50?
My collaborators do.
So this is something you have to, 50 definitely give you very good contrast. You can see everything clearly. But first of all, those ribbons gonna be very fragile. And then you have to make sure it can actually stick to EM grid afterwards. And also the information in that thickness is gonna be limited. So this is a balance you have to choose depending on what you want to do. So this is also for practice. This is one of the ribbon I did many years ago. So to make that ribbon took me a long time. This is actually cyanobacteria. We froze them in a very big piece of vitreous ice, and then we put it, did the cross-sectioning as I showed you in the movie, and then I was able to stabilize it on a piece of EM grid and then make that tomogram. But this one is probably over 100 nanometer. So by looking at it, it's very wavy. It's not very flat. So some features come from some sections, and then not always showing you flat surface. Okay. And also this is E. coli. So also by high pressure freezing and sectioning. I just want to point to you some of the artifacts from this technique. So first of all, this is the knife mark. So the section is going that way. So it's diamond knife, but it's not perfect. So it always leave you some of those marks going along the direction of sectioning. It will always be there. And then those are contaminations, probably during your multiple moving from one station to next station. So ice crystal deposit on that. This is actually pretty clean ribbon, I think, already. I usually see a lot more than that. And then also, this is the crevasses. Those are because, you know, the surface tension, when the knife goes through, it creates those darker, granular looking artifact, so that on your ribbons. So I think this is interesting. So this is my project. It's the same cyanobacteria. This one, I was able to do it, basically do tomography of the whole bacteria. This is one of the small cells. And then you can tell the contrast is not really good. But the cell, the membrane is very smooth. So it's very healthy looking. And this is from one of the sections I can show you. So first of all, you can see the shape are not the same. So the sectioning, high pressure freezing and sectioning change the overall shape of the cell a little bit. And also this one, I'm pointing to it, it's a carboxysm. Carboxysm should look like a phage, exoheterophage, but it's definitely not. It seems like compressed a lot through the knife sectioning direction. This is the known artifact, compression in sectioning. But still, don't get me wrong, this is still a very useful technique. For example, if you want to cut open a cell and then to look at all the detail in there. So many facilities, they have a high pressure freezer, they have a cross-sectioning, especially for patient sample. This is still very useful technique to give you very interesting information to cell biology or pathology.
How much damage is done at the protein level, do you think?
So people think you can do subtomogram averaging on ribosome, right? That's, I think several papers I see people published, they did seems like ribosome is very resistant to the compression or the artifact. I haven't seen people to do anything subtomogram averaging on other protein complexes. But just look at the carboxysm, look at the shape. The physical, artifact or physical damage isn't quite. But I still think this is a good technique to look at the overall organization of the cell, the architecture of bigger objects. So in terms of small protein complexes, structures, details, high resolutions, I might find alternative approaches to do it. So, but it's good for something. It's still, very widely used in many facilities, I believe. So that's everything I want to cover for sample preparation, specific to tomography. Is there any question? Yes?
What kind of protein coatings do you use to grow your mammalian cells on this grid?
I'm sorry, say that
You
again.
mentioned you use protein coatings to grow your mammalian cells.
Oh, that's very cell specific. Polylysin is my favorite one. So if I have a new cell type I want to try, I usually just use polylysin. No special reason. It worked with many cell types, but for some cells, maybe other coating protein, collagen for example, there are a list of proteins you could try, and also concentration.
Usually people in the literature have grown those cells on other things. So I just start with whatever people have done in cell biology or optical microscopy papers.
But at least double the concentration.
Yeah.
So when you play the bottom of a flask, or you coat EM grade surface, they are very different. The cells really grow not that healthy on that.
Have you used silicon nitride grids at all in your lab?
Silicon nitride.
They make EM grids that are compatible with EM grids made out of silicon nitride that are basically glass. They're a little hard to clip into autoloaders, but
I use silicone.
they just have like these giant windows in the center, and then
Oh.
a continuous like film that you can get down to
What
5
film?
nanometers.
What-
It's silicon nitride.
silicon
And you can etch the glass if
Yeah.
you want. Try to
So
do that.
I use silicon dioxide. It really look like just glass.
Hmm.
And then it's actually give you, if I have a new student, I let him or her use silicon dioxide because it's not that easily broken as carbon film.
Hmm.
And then we feel the EM where they actually feel a little bit sturdy to handle.
I haven't used silicon dioxide, but I've used silicon nitride.
Basically,
It sounds similar. Yeah.
sounds
It kind of just looks like glass, but
right,
in my experience, like growing cells on like a glass cover slip,
right.
silicon nitride grids seem to work about the same in terms of like how much coating protein I need, how long they need to go.
Where did you go to buy that type of grids?
There are, I think EMS sells them. They're usually back ordered, and there are a couple of
Always
there.
back-ordered.
Yeah,
They're
there are a
always
couple
back-ordered.
of companies that specialize in like making things out of silicon that have
Mhm.
started to make these grids for EM.
I-
Elizabeth Villa uses them a lot.
I
and likes
use
them.
silicon dioxide grids
Mhm.
a lot, also from EMS, and then always back ordered.
Yeah.
So-
Everything from EMS.
Yeah, and then they work better for some of the cells compared to carbon film. So that's the fun details for your cellular tomography project. Any other questions? Okay, let's go to our case study. Lots of questions we have to go through. So I pick up this paper. It's called Correlated. It's a palm study and then followed by Cryo-EM of bacteria. So the goal of the project is to find the type 6 secretion system from one bacteria. So those type 4 secretion system, they're like an intracellular tubes in the bacteria. You don't have that many to start with. And then the diameter is maybe 10 to 20 nanometer in thickness. And then the goal of the project is go into the cell, find that tube, and then resolve the structure. So to do this, so you can imagine, first of all, location information would be very important. So what they were able to do was they culture the cell. They use fluorescence to tap that protein, and then they use fluorescence signal to find those tubes, location of those tubes. And then after that, they will apply tomography, Cryo-EM, tomography to it to resolve the structure. So why I pick up this paper? So this is still one of the very few applications. I don't know how many years old it is, several years. But it's still one of the very few applications applying super resolution fluorescence imaging in correlation with tomography. So CLEM application now is not that rare anymore. So many facilities have it, many labs are doing it. But still there are resolution gap between conventional fluorescence imaging versus tomography. Conventional fluorescence imaging, you can zoom into 200 nanometer. That's the limiting resolution. But for tomography or for EM, you're probably looking for something, in this case, maybe 20 nanometer or less. So you may not be able to precisely find the location to direct your tomography study. So I think this is still a very interesting paper, although it's several years old. I don't know, anybody know other higher super resolution application? No?
Not super.
I know Brown Colster was doing something along this line, but I don't know if his papers.
It's one of the only papers I've seen where people trying it, but
Successfully trying it.
yeah, like as far as published examples.
So you know this paper?
Yeah.
Okay, good. So cell culture easy, I'm not gonna go through. And then they also put a protein of interest, it has to be photoactivable fluorophore for the super resolution application, right? And then I think this is very interesting. So first of all, you want to find a fluorophore that actually work in very low temperature. So many of the fluorescence protein, their performance in liquid nitrogen temperature is very different than in room temperature. So the photo-bleaching will be delayed. And then you basically, this is a comparison of performance of the fluorescence protein in room temperature versus cryo temperature. So you want to see before the laser activation, no signal. You want to make sure your laser can be activated, photo activation after laser, and then make sure before and after are clearly different. In room temperature, it seems to be okay. You have many targets, potential proteins you can use. But look at liquid nitrogen temperature. Either they don't have a lot of activation, or they're always very bright, not photoactive. So the winner happened to be GFP, photoactivable GFP, is before you have very weak signal, and then after activation, the signal is pretty clear and strong. So they did this comparison, they did this test before they know which protein should be used in the lab. I think this is one of the technical details that are very important for success of this project, right? So once they have that construct, they did some function analysis, immunoblotting, make sure your target protein is there and is active, is functional. Then they use the regular Plunge freezing using an FEI visual light. I don't know if you have a visual light here or not. But
Mark
Mark 4, okay.
And 2, we have a Mark 2 and Mark 4.
Okay. Yeah, this is a bacteria, only maybe 1 or 2 microns. So it's perfect for Plunge freezing application. So after that, small detail. For this one, they use the macro grid instead of conventional like the square grid, because those macro grid, they have letters or they have numbers. You can see them as address, so that once you have a fluorescence signal, you can use those address to find the target once you load the grid into TEM. So this is something. See. So if you want to buy silicon dioxide marker grids, that's extremely hard, and then the waiting time is very long. Okay. And then cryo pump. This is the one of concept checking question in your syllabus. So what is cryo pump? And then factors that limit the localization precision in this experiment. So PALM is photoactivated localization microscopy. And then I have a slide really quickly to show the fundamental idea of PALM. PALM is basically a sequential activation of a small subset of your fluorophore at a given time, because only very small subset is activated at each given time point. The chance of the signals are overlapping will be very low. So what you do is you have the sequential activation fluorophore images. At the end of the imaging session, you computationally adding them in so that you have the fluorescence image of your target, but with better resolution just because the signals are not overlapping. Okay. So cryopump is basically cryo application in cryo temperature. So this is one of the supplementary figures from that manuscript. They show you what they did to the cryo stage. So basically, it's a pump microscope with a very special liquid nitrogen cooled cryo stage, so that you can keep the sample in liquid nitrogen temperature during the imaging process. And then you also, because the sample is kept in very low temperature, you have to make sure the working distance of the objective aperture is long. Okay? And then they did some tricks to control the laser power to minimize damages. But even that, the sample is slightly damaged compared to result. This application, I will show that later on with one of their movies. So room temperature versus cryo. What are the advantages and disadvantages? Advantages, room temperature. Nobody saying anything. So I already mentioned because
Well, I mean, I'm assuming room temperature doesn't require a special setup that requires nitrogen flow, compensation for heat transfers.
slightly easier. Okay. Right, that's true. And also, I also mentioned some of the fluorophore performance in room temperature are actually a lot better than in cryo temperature. And then the setup will be easier. And what else? Oh, you can also use all your immersed objective lenses. So numeric aperture gonna be bigger, so better resolution. Right. I didn't say the easier setup, I will put it back here. Okay, for next year. So cryo temperature, one thing good about cryo temperature though, the sample preserved, they're not gonna move, they're gonna be very stable being there during the imaging session, right? I think that's one advantage of the cryo temperature. So the bonus question. So the factors limiting correlation or localization precision. So it's basically it's the resolution of the image, and also you're correlating the image you're taken from light microscope versus electron microscope. That's two completely different imaging modality, right? So the image, for example, over here, taken from the two microscopes, the shape, size, and center are going to be slightly different. All those going to affect your correlation, how precise your correlation will be. Right? And then data collection. Now is the fun part. We're moving on to EM. So they don't, at that time, a couple years ago, they don't have cryos in their facility. So the microscope they use is called Cellular. Cellular is also a 300 keV electron microscope, and they also have a cartridge system to load your grid in there, but it's a bunkier cartridge system compared to the auto grid we have for the Cryo system. And then I believe one time you can load, instead of 12 grids, you can load 3, right? Okay, then 3. Then they also, the camera is the K2 camera they're using. They're using direct electron detector already. So those are very easy. I'm not gonna challenge you for this. Just the image you take. And then range. So range, usually people do 60 to 60, 70 to 70, and maybe 80 to 80. I usually don't do. Mostly because, majority of some of the microscopes, they allow you to do 80. Do they, Alex? Wales? 70 to 70?
70s usually.
But the Gatan, they have that special side entry holder, allow you to do 80 to 80 degree.
I think it'll be for room temperature, right?
Also
Not
for
cryo.
cryo. It's
For
also
cryo
for
too?
cryo. It's a very special
That low
small
profile.
With the low profile is but at what's angle.
So in the facility I used to work in, they have their special Gatan 80 to 80 special holder, set entry holder. But I choose not to use it. It gives you the actual range. But think about it. When you tilt your sample to 80 degrees, like almost perpendicular, the ice is really, really thick. You don't see anything. Not much. Very dark. So when you tilt to 60 degrees, the thickness is doubled already from geometry, right? 80 degrees, a lot, maybe 3 times. Big calculation, somebody can tell. Not worth it. You're wasting lots of effort and time and those on the image that actually not giving you a lot of information of your sample. but this is some of the sample geometry, goniometer restriction, all those factors will affect your decision. You know, what range you want to do in your project. A missing match, everybody know missing match, right? Because you can't do the whole 180 degree. Okay. What is your centric height? So, I remember one of you said you actually used a microscope before. Which one? I don't remember.
I did.
What is your centric height?
Said if I really did what it was. I don't know.
Okay.
It's the height of the stage that you can tilt it without the sample.
Right. Right. So I put this is the screenshot from the Grant Jensen tutorial. So basically, when the sample is really aligned with the goniometer axis, so this is the side view of the microscope. This is the column. And then this is the objective lenses. And then you're really looking down the sample airlock. And then the pink, this is the center of the axis. You want your sample to be exactly at this level. Because, for example, if you're going up, when you tilt, you will notice it's actually the sample moving, as he said. So this one, then what is the tilt axis offset? Once you understand what is your centric height, this is very similar to that concept. So your centric height is your position of your EM grid, your sample, and position of the goniometer axis. Your centric height is up and down. And then the tilt axis offset is left and right. So it's both because the goniometer, the axis of goniometer is not in perfect alignment with the tube that you inserted in. So setting now, you load your sample into that Cellular microscope, and you already aligned your microscope. Now you're ready to go to set up your imaging condition to collect your data. Now what is the factor you have to consider? What MAC you want to do? And then also how much dose you want to apply to your sample. Then you need to decide your tilt increment. You want to do 2 degrees, 3 degrees, or 1 degree, 0.5 degree. And then details. For example, if you want to do dose fractions, you just want to do counting. And then you want to set up your dose rate, and you want to set up your defocus. There are many parameters you need to set up. For example, magnification. This is a very simple one. So how do you set up your mag? Depending on the pixel size you want to look at, right? How much detail you want to see. But is it a good idea you just keep zooming in, apply very high mag? Is there any bad thing if we just go very high mag? Your view.
Dose, anyway, dosing more of the sample.
Yeah. Yeah, that's one consideration. What else?
Missing weights. Missing weights. Sorry. Missing weights will be a consideration.
Missing match, missing match will always be there.
But if you go zooming more, if you go higher magnification, you crop in more view.
Right, view gonna be smaller. And also, really, is it necessary to go very, very high mag or not? Because what is the current resolution of a tomography, tomogram of a cell, for example, region of the cell? How much you can see? Is it necessary to really zoom in to look at 1 microtubule? Will you be able to resolve that resolution after data processing? And then also depends on what is your target. What is your target? In this case, they actually didn't say what MAC they use. They didn't say what pixel size they use. But we know the target they want to look at is about 10 to 20 nanometer. I don't know their MAC. They didn't say in the paper, but I would pick up something maybe 5 point something asteroid pixel. Or slightly lower, 3.5-ish. I wouldn't go higher than that. I think that is very good for the target already. And then going really zooming in, you limited your view. And also, after alignment, also the missing match, the error building in during alignment, you won't achieve a 3.5 astral resolution map anyway. Okay?
So what she just said goes back to the lecture last week. If you guys remember Lorenzo talking about the Nyquist limit of your image. So picking magnification and pixel size is. Do you have any questions about that when you're setting up your data collection? Think about
Exactly.
the Nyquist limit.
Right, exactly. I usually a little bit more conservative. If I want to say really look at something 20 astron, I'm probably going to divide that number by 4. Say starting the first session 5-ish. 3 is also good. No need to go higher Mac than that. It's just me. People have different preference. And total dose, there's actually not much you can say about total dose. You just try it. Different sample have different dose tolerance. Some are more tolerant than others. They use very high in this one. Also, you have to consider the sample has been imaged by laser already. And then after that, they're giving it 180 electron per astral square. It's a really high dose, I think. And then the range, they're doing -60 to +60 with 1 degree increment. So how you decide? Tilt step and angular sampling. How many degree, how many images you want to take? What factors we have to consider? If nobody speak up, I'm just going to randomly call somebody. Like Alex. Yeah.
Most people's answers is whatever Alex says to do.
Right. So, you know, the
It probably goes back to like your resolution goals or like what size or what angles you need to determine the features.
so see the angular step is in positive correlation with your resolution. So if you look at the table for a project for sample of fixed size, basically the smaller the angular step, the higher, theoretically speaking, the resolution will be, right? But that's not the only factor you have to consider. So as I mentioned in my previous slide, there are only that many total dose, electron dose, you can apply to your sample, right? So if you're taking let's say 180 electron per astron square, you can use on your sample. Do you want to take 60 images with 3 electron per astron square per image, which probably gonna give you a pretty good contrast, clear image of the cell. Or you want to do like they do, like a 1 degree increment. That way you take 120 images, then each image you have 1.5. So this is also something you have to consider. Also, you have to think one more factor. After this, do you want to do subtomogram averaging or not? If you want to do subtomogram averaging, maybe you want to have each image better signal so that you can do a very good alignment. You're gonna have a very big gap in Fourier space from one image to the next one, which actually doesn't matter that much because eventually you will be able to fill that gap from different particles. But some people don't agree with me, say, you know, you want to make sure cover as much range as possible, so the mismatch is going to be smaller, right? And some people say, I just want a very good image of the particle in low tilt only. For example, 40 to 40, minus 40 to plus 40. That way, those are used on the images with better information, better signals. Low tilt give you more structural information than higher tilt in general. So,
To Do they do any more? I don't hear much about doing the rotation, the 90-degree rotation to help fill the missing wedge.
mesh? Yeah, they do. I have a slide to show. Can I get out of PowerPoint?
Oh, that's it. You can do it later.
No, it's a. Okay. You brought it up. We should just go over it. So missing match. So missing match is actually one of the limiting factors in tomography. This is actually relevant to the discussion we have. So first of all, missing match. This is, for example, is a polysome tomogram. From XY view, it looks perfect, good looking, right? But when you tilt it, you see in the Z direction, a spherical object become a football because of the mismatch information. And then what you can do is from exactly the same data, and what you can do is you can cut out individual particles and then do subtomogram averaging. After alignment, you were able to compensate for the mismatch. And then from the subtomogram averaging, you don't have that artifact anymore. And then another way to do it, as you mentioned, is the dual axis. Dual axis, what you can do is, this is a very spherical object, and this is the mismatch after reconstruction. You can see it very clearly, X and Y, and then in the Z direction. Really you have missing information and stretch a little bit in the Z direction, right? This one is also very close. So this is the, after the dual axis, basically the idea, so people know the dual axis tomography, right? So you basically tilt in that direction. So you have a missing match, for example, like in that direction. What you do is you actually tilt 90 degrees and then do it that way. So instead of a missing chunk of a batch of information, you're missing a smaller in space, smaller range, not a batch anymore, missing whole information. That way the artifact will be a lot smaller. But I said this is a very good question and it's very relevant to our discussion at that place. Whereas, think about it, you have 180 electrons for the whole sample. If you want to do dual axis, you have to divide the total dose by 2. And then use the first half on one tilting angle, right? And then use the second half for the second tilting angle. Assuming you keep the same imaging condition, each image, the dose is only 50% of what you have. With that, your signal to noise ratio is gonna be higher. Alignment will be more difficult. Errors, potential errors to build in will be higher. But you do have a smaller mismatch. It's start from a mismatch to missing point. So you get something extra when you're missing something. Right?
There's also some people who think that dual axis holders aren't as stable.
Yeah, but you say tomograms are a way to, I guess, fill in that with using less dose?
You have to take more images.
But I mean, less
Right.
than doing a 90-degree.
So-
You would use less dose doing a sub-tomogram rather than doing a 90-degree rotation. Okay.
But you'd have to collect more tomograms of different particles to be
To
able
fill it
to
in,
add
yeah.
to the multi-tomogram.
Yeah.
Okay.
Yeah,
You have
if
to
you
collect a lot of
want to
data.
do subtomogram averaging eventually, you can collect more particles and compensate for missing match that way.
Yeah, so once you have a general idea of what it is you're looking at, you can then do so, yeah.
That's the key. If you know what you're looking for,
Yeah.
then your target happen to have very strong structure signature for you to find it. That will be
And
good.
occur in abundant enough numbers.
Oh yeah, abundance. So
If you're
that's why
doing-
ribosome is a really good
Yeah, because there's a lot of them.
sample.
But there are a lot of protein targets that in bacterial cells you might only have a couple of proteins inside whole bacterial cells.
Like this one. They have only like a couple of tubes per cell.
Is dual type imaging ever preferred over the regular type of imaging in any case?
Tube being
Duh.
no, Tubing or dual access?
Dual axis.
Dual access, I believe the microscope here you can do it. So what they do is they basically have a holder system like that. And you hold your EM grid like this, and then you tilt like that. After you finish the first one, you go that way. And then your sample you become this, and then you tilt.
I'm saying is it preferred, like for the subtomogram averaging?
I actually don't. I think it should be the opposite. If you don't do subtomogram averaging, you just want to look at the object, missing match really gonna mess up your view. You might want to try that. It justifies trying it. But if you want to do subtomogram averaging eventually, why not just collect more particles and then compensate for missing match by combining information from more particles? That way, each particle you have more information in each frame of image, give you better alignment, lower error, and then better resolution for each subtomogram. I would recommend to do access. I
Most
don't know
people do
if-
single axis here.
Hmm?
Is that your
That's a
experience?
question for
Jen?
Alex.
Yeah,
That's all we got.
that's all we ever do. Nobody really does dual axis much.
It was a very popular topic back, I don't know, 5 years ago, 6 years ago, or 10 years ago. 10 years ago. It's a.
He has a lot of
Stability's
practical
better with
difficulties.
single.
You have to
Now
retarget
it's-
after the rotation.
Yeah.
If you mess it up, then you've blown. You have only half the data dose from your.
It used to be very difficult. So for the Polaroid microscope, it's gonna be very difficult. So what you need to do is image it. They are on a very different stage. So what you have to do, you have to take the grid out, and you have to turn the grid, physically use a tweezer to turn the grid 90 degree. And you have to load the grid back to the microscope, find exactly the square you imaged, and then do tilt. During the process, many things could happen. Contamination, and then temperature goes up. Your grid is not good anymore. Or you bend it. You puncture a hole right across your square using your tweezer. Or you can't find it afterwards. So there are many issues. But nowadays, it's not that difficult anymore. I think the microscope here, you can just, as I said, it's a one-click button. And then finding it still probably takes some effort. But technically speaking, it's not as challenging as before. I think that's like years ago when people first started tomography. Missing match was a very big concern in the field. And people were trying very hard to fix it. And then subtomogram averaging started a lot later than tomography, just tomography of your sample. So probably people were thinking dual access is one solution to the missing match. But later on, people can do subtomogram averaging and then to compensate for missing match. And then also because of the splitting of those in 2 tilt series instead of 1. So it's a balance. So defocus is another thing, another factor you have to consider. But this is the same principle as in Cryo-EM single particle. You want contrast or you want resolution. So this one, they want to make sure they see everything clearly. So that's why they use a relatively higher defocus. -10 is pretty high. Okay, and then data collection. So they use the USF Tomo package to collect data. So when tomography first started, people manually turn the stage before they take a next tilt image. So I highly doubt it anybody is doing that right now. So there are many softwares allow you to do automatic data collection, and then people use Laginum, Zero EM, and then Thermo Fisher have their own software package you could use, but they're all automatic. So that's your question. So when we talk about automatic data collection, what is tracking, and then what is targeting. So tracking is very easy to understand. So you have your object, you want to tilt, take an image, tilt or take image. You want to make sure your object is always in the middle of your image, under your view. And then keeping that object always in the middle of your image is tracking. And then what is targeting? So automated data collection means we'll come in 9 a.m. to the lab. You can pick up on your EM grid different locations you want to image. And then once you set it up, you can go home at 5 p.m. The microscope will be able to go to one location, take the tilt series, and then can automatically jump to the second location and take another tilt series. So from one location to the next location is called targeting. You want to make sure the targeting is very accurate. Otherwise, your first tilt series is perfect. The second, if it didn't go where it's supposed to do, then you will be in trouble. You're not going to have a tilt series of your targets. So the USF Tomo, there are different algorithms behind the automated data collection. So I don't think people don't seem to be very interested in this. I'm just going to go through quickly. So
So the tracking, that compensates for the axis offset, the tilt angle axis offset that you were talking about earlier. So that changes the XY position as it goes through the tilt series.
it change tracking mostly in this particular case. I think is mostly translation. I'm also focusing XYZ. Yeah.
Okay.
Right.
For
Right.
predict-
Right.
So once you calculate, like you send your the axis offset of your XY position, then you can like calculate using geometry to predict the track on that.
Yeah.
Okay.
So he basically, have a very good explanation for the predictive method already. I put a box over there because this is the mechanism algorithm behind the Tomo software they use in this paper, exactly as he mentioned. So what they do is you put your sample in there, and then zero tilt, you center it, you take one picture, and then you tilt, take another one, and then you tilt, take another one. Once you have a couple of parameters in terms of translation and also in Z defocus, you can build a model based on the several data points and predict what's going to happen when you tilt to next one. And then you computationally compensate for that shift and then defocus. And then you don't do real measurement. You just predict what's going to happen and then compensate for it and then take an image. And then Liginal is like that. So it's very fast. You want to have a very good microscope for that purpose. Make sure your prediction model is accurate enough from very limited number of data points. So all microscopes right now, I think pretty good for that purpose. Liginal is predictive. Yeah.
All 300 kV microscopes. 200 like our F20, T12. Not good.
Oh, ours is 200 kV. It's pretty good.
You have an article.
I have a.
Yeah, that's good.
It's the stage. It's the stage
It's the
design.
stage.
So the 200 kV microscope we have at Rutgers is basically the same compute stage, the same sample loading mechanism as the 300 kV, and that design is really, really stable.
We collected tomograms on the F20 all the time.
Serum.
No, we're
No.
large enough. And you were like, oh, how did this work? This is definitely work.
It's rare.
The
So it's rare.
TF20 is the Gatan 626 side entry open, and you use Liginal,
Yeah.
and it worked.
Yeah.
Depends on which holder we use. Some
Okay.
holders have a crazy option.
But another very popular program in the field is called Cryo-EM. It's free, so many facilities are still using it. That one is focus position method. So anybody need to go through this. So basically what you do, you know where the tilting axis is, right? So you set up a position, you find a target, perfect. you put it in the middle of your view. And then you go draw a line, parallel to the tilting axis, and maybe several microns away. You set up as, I'm just safe, set up as tracking, for example. So because the line drawing from tracking to your imaging is parallel to the tilting axis, so the transition or translation on your imaging area and on your tracking area should be the same. So when the tracking area, after tilting, move left, your imaging area should also move left, exactly the same amplitude, right? The same number. So what you can do is, you don't want to waste your dose on your imaging area. What you can do is, you take an image, for example, 0 degree, you tilt your stage, and you go to tracking area, take an image. Use that image to compare to the reference image of tracking area you take at 0 degree. Let's say it moved 1 micron left, and then your imaging area should also move by 1 micron left. So you compensate the stage, move the stage 1 micron right, and then you go back to imaging area and then do it that way. Take an image and then tilt again. So that's the fundamental idea of Cryo-EM. So compared to the predictive method, you have to, jump in between tracking and your imaging area at least couple times for every tilt, right? So it's gonna be longer to finish one tilt series. But if you have a tip 20, as most people do. Okay, any question about this?
Isn't that what guitars putting in the metronome?
Yeah, metronome will have at least one focus position method.
Yeah, I thought it was a little hybrid now. I thought Ceruleum also does a lot of modeling and prediction too.
Yeah, it's hybrid. If it goes off, then it will go.
So, many of the program is a combination of the two, especially for the focus position. If you do predictive, you can do predictive alone. And then if you do focus position, most of the programs are a combination of the two. They have a holder file. They know their stage, their holder, how much they're gonna change for each tilt. They build in that number before they do tracking. That way you're gonna have very small range of transition translation from one tilt to the other. So how to do, I think most of you have done data processing already. So when you align a tilt series, there are several parameters. You basically make sure the image taken from one tilt in X and Y position align perfectly to the next tilt. You want to find the geometry of your tilting axis, where it is, and then what is the rotation angle, and then also magnification. You want to know defocus. Magnification is relevant to the pixel size, and defocus is relevant if you want to do CTF correction later on to improve your resolution of your subtomogram averaging. So this is the movie they have at the end of the project. Light microscope. That's a cell. Zoom in to look at the photoactivation of the fluorophores. It's like a blinking sequential activation of different subsets. This one is when you zoom out to look at the whole cell. This is a geometry. Pay attention to the eyes. The eyes is actually not that virtuous anymore. Look at the eyes quality. But they have a very interesting idea in the paper. they say the cell actually can serve as a like buffer. So although the ice close to the outside of the cell is not that good anymore, the inside of the cell, in theory, actually is pretty okay. You can still see structural details. They're really good looking. See, when you zoom up and down. Vibrations are everywhere. That's the two tubes. One is in contraction, one is in extended form. The diameters are slightly different. To be honest, because the orientation of the two tubes are not really parallel in XY orientation, I think, by looking at the section slice views, if we don't have that polarization marker, your confidence level will really be low. Finding out those two tubes and naming them the type 6 secretion system. So I think this is really a very, very good paper and a very good project. And I'm really impressive they were able to carry it all the way from beginning to end. It's a good paper for our discussion. So this is the slide view. I have just a probably a couple of slides on annotation and data visualization. So is there any question so far in alignment? Okay. So annotation. So once you have your pretty tomogram, you want to show different views, show all the structures in there. So in that movie, they showed mostly the slice view. Basically, you have a 3D object. You show it slice by slice. You find your object. So also there are other ways of showing off your data. One of them is called volume rendering. The other one is called isosurface. So I actually have a movie from my lab. On top of the slice view, I have volume rendering and isosurface. They're gonna be very. This is the slice view. This is a PC12 cell, and then that's the whole of EM grid. And then now I started by showing the slice view. This is called volume rendering. To basically show every voxel in the 3D density. And then you basically see through everything. Each point is a number density. And then isosurface is something you define a surface level and you apply that number to the whole density. So it's like a shell based on that number. So the mitochondria, microtubule, and all the vesicles were displayed by isosurface. So once the volume rendering is gone, you will be able to see here. That way you will be able to see how everything interacts with everything, to really look at your tomograms in 3D view. You can zoom in, you can dive in. So this is the advantage over slice views. It's a real 3D annotation of your data.
So how does it identify the isosurfaces? Is like the density or the value of the voxels, or is it connectivity of the...
So you can think of like in 2D, right? In 2D, if you have a map, basically if it's 3 by 3, you have 1, 1, 2, 2, 3, for example. If you set a threshold of 2, for example, any square with value smaller than 2 gonna be 0. And then you basically draw a line along 2. That's isosurface. It's called isoline in 2D. The same idea in 3D. That's how you show.
Okay, so it's kind of like looking at a density map.
The appearance will be different depending on the threshold you set up. So generally speaking, lower threshold give you bumpier density looking, but the map is the same map. And then volume rendering will be a more realistic presentation of your data. You're basically looking at each voxel by value. Any question? And then automation. I don't have any answer in this slide as I do for others, because this is something different scientists, different facility gonna be very different. So, for example, over here, what is automatic? What you have to do it manually? Sample preparation, is it automatic? You have to apply your sample to the EM grid if you want to use visual blot. If you want to use spotted on, you have to put that tube. I don't know how to use spotted on. You have to say something.
You put your sample in a little tube and then basically press a button or a series of buttons.
Okay, semi-automatic.
If you get VenCat, it's totally automated from your perspective.
But
No, the new commercial version is very automated. You don't really, it'll put grids in grid boxes for you after it's frozen them. So
that's actually really nice,
Yeah.
right? Many of the
That's
grids
great.
were damaged at that step. You know, when you grab it and then want to put it in a small slot in your button,
Yeah.
many of the grids were bad that way.
Yeah.
And some of them they basically attach to your tip of your tracer. You just cannot get it drop into the box. But that's nice. So currently sample preparation semi-automatic, and you have the grid. You have to manually transfer it to an electron microscope, and then loading. Once you clip it, load it to the microscope, changing grid. You have to click a button, but pretty much automatic. And then once you have to manually check your grid to see the quality, to find your target. And then you do that from 9 to 5 every day. You pick up your target, and then you go home. The microscope will be automatically collect your data for you. And then I believe here you can also automatically do the frame alignment
On the fly.
on the fly. How about that? Tomogram alignment reconstruction.
Depends on your sample.
Okay. You can always do it. Work or not work is sample dependent. Quality of the images, how thick they are, the contrast of the image, the quality of the image. And then, but even you can do it on the fly. You can do it batch, do a batch processing by iMont or by not and then after that, once you have the tomogram, and then annotation really is not automatic. You have to know your biological story. But in my dream, what I want is I have the sample ready. I'm okay to prepare sample to make the grid perfect. I want everything to be automatic once I pass that to something, to a machine. And then I'm okay to take it out of the plunger to the microscope. I want the output from the microscope on tomograms, and then I will enjoy my life preparing the sample, do the transfer, pick out my area, and then do data analysis. I think that's ideally what I want. This is a boring slide. And then annotation, template matching. So this is something I said I prefer to spend my time on. Once you have your tomogram, what you want to do. first of all, you want to find your target from a tomogram. How can you find it? How do you find your target from tomogram?
I just look at it visually to see like what I want to look at, and I
Mhm.
pick that area, and I pick it in multiple areas, and I say tomogram knowledge.
But basically, you know what you're looking for.
Yeah.
You know you have a model, you have a structure, probably from purified protein complex or X-crystallography. You have a template, and then this process is called template matching. Okay. You know your structure, you go into a tomogram and you find it. And then what target is easy, what target is hard in template matching?
Ribosomes are easy.
Because
They're everywhere.
and
They're round.
they're large, relatively large, right? They're everywhere. Yeah, with new structure and large, and they're everywhere. Easier to find. And then visual proteomics is basically is in the data mining aspect. So generally speaking, cellular tomography, once you have the tomogram, they're very information rich. You might be only interested in one of the project, one of the protein target, but there are thousands of others in your tomogram already. So maybe you can reuse your data, publish more papers than one. Okay, the limitation we covered the missing wedge already. So another resolution limiting factor in tomography, we kind of covered also. Every sample, they are only tolerate to certain number of electrons. You have to know that number. Make sure you don't damage your sample before you look at it. And then negative stand really depending on how good the reagent is, how fine the granule is, and the fidelity of the standing process. And then resolution limit, as we discussed the factor of the tilting increment. You need to decide really what is your goal of resolution, be practical, and then define your magnification, which is your pixel size, define your tilt increment, and then think about the missing, always remember the missing wedge artifact when you interpret your data in tomograms. And then defocus is a balance between contrast and resolution. And then alignment, you want to do very good alignment. Make sure one image in tube series very well aligned to the next one in terms of XY transition. And you also want to make sure you define your tilting axis, rotation, and position very nicely. And then that's all we want to cover for today. What time is it? Perfect. Thanks. Okay.
So for the students, Micah, do you want to talk about the practical?
We have our first practical on Wednesday. So this is our microscopy practical. We are going to be going over a sort of fast version of the alignment of our T12 microscope. It's our 120 kV screening scope right over here. So we're going to meet here at 3:30, same time as the normal lecture. Then we'll just head over to the microscope room and we'll look at aligning the gun and the condenser system. And for the students taking it for credit, there will be a small worksheet that you have to fill out and turn in the next week.
Okay. That's the slides will be posted quite soon. If you have any questions, you can always email us. We'll forward them away. Or if you can email her directly, that's perfectly fine. I'm assuming it's perfectly fine.
It is perfectly fine.
Okay. Well then, we'll see you on Wednesday. And you'll actually see a microscope. And you get to touch it, sort of.
Oh, they haven't touched a microscope yet.
Some do.
Some have.
Some have, but